now that we've seen a whole bunch of properties of the Laplace transform, I want to introduce to you the concept of the inverse Laplace transform. Now, the theory of inverse functions, obviously, if you have the inverse Laplace transform of the Laplace transform of some function, f of t, if this inverse is any good, we should be given back our function f of t. So this is, in essence, the definition of the inverse Laplace transform. The inverse Laplace transform in theory is simple. As you can see, I wrote it down in this one line, but in practice it can be slightly more difficult to actually compute an inverse Laplace transform. But we'll see that in some cases it's not that bad, and in other cases you need to do a little bit of algebra. So let's look at a not that bad case. I'm making this up as I go, so see how it goes. The inverse Laplace transform of some function, let's say 6 over t to the fourth. What is this going to be? Well, we notice there's a t to the fourth down there, and there's a 6 up there. This kind of looks like what we had for our, oh, this isn't, excuse me, this isn't t to the fourth, this is s to the fourth. This looks like what we had when we had a polynomial, because when we had a polynomial, the Laplace transform of the polynomial was s to the n plus 1 over n factorial, and n equals 3 looks like it'll make this work, t cubed. And this is actually the solution because Laplace transform of t cubed equals, again, 3 factorial, so 6 divided by s to the 3 plus 1 is 6 over s to the fourth. And that's exactly what we have up here, so it works. Alright, so that's first inverse Laplace transform. Good job. Let's see if we can find a different thing, maybe the inverse Laplace transform of s over s squared plus 81. S over s squared plus 81. We have this s squared plus, it's a square number, perfect square even. This almost reminds you of cosine, maybe. So what this could be, maybe, is the cosine of, and then what would it need? Well, cosine, if we remember the Laplace transform of the cosine of a times t, is s over s squared plus a squared. So if this 81 has to be a squared, then a has to be the square root of 81, so 9 times t. And indeed, this is actually it, because again, the Laplace transform of the cosine of 9t is just going to be s over s squared plus 9 squared is 81. So you're trying to find, whenever you take an inverse Laplace transform, you're just trying to find the function whose Laplace transform is the input to the inverse, just like for any inverse function. Alright, so these are the simpler examples of inverse Laplace transforms. You can try a few on your own if you feel like it. Where it gets a little bit more difficult is when you have the multiplication of two functions in your inverse Laplace transform. So if I wanted to take, for example, the inverse Laplace transform, getting this out of my textbooks, let's see how this goes, of negative s minus 7 divided by, and then we have s plus 1 times s minus 2. If we want to take the inverse Laplace transform of this, we don't really have a method to do this because we don't have a function whose Laplace transform specifically is something over and then a multiplication of two rational functions. We don't have that. So what we're going to have to use is a method that we learned in algebra. In algebra, we learned partial fraction decomposition. Partial fraction decomposition. It's like compost. You're decomposing. Partial fraction decomposition. And partial fraction decomposition tells us that if we have some rational function, how we can say, for example, make negative s minus 7 over s plus 1 times s minus 2, how we can turn this into something over just s plus 1 plus a different something over just s minus 2. And if you're a little bit rusty on partial fraction decomposition, I would highly recommend that you brush up on it. When I first learned about inverse Laplace transforms, I myself was a bit rusty on partial fraction decomposition, and there is a lot of partial fraction decomposition when computing inverse Laplace transforms, so I will warn you, but I'll go through this one. And actually, this method, partial fraction decomposition, where we just try to get some unknown thing over just the first part, plus a different unknown thing over just the second part, this is actually just all partial fraction decomposition is. Now we just solve for a and b, and hopefully it'll work out. Alright, well, let's see if we can solve for it. I'm going to come up here so we have more space. What we're going to get is if we multiply out s plus 1 times s minus 2 on both sides, we're left with negative s minus 7, the left-hand side, and then times a, and then s plus 1, 1 over s plus 1 times s plus 1 over s minus 2. The s plus 1 is going to absorb the other s plus 1. We're just going to have times s minus 2 here on the a, plus b, and then the exact same thing but opposite happens on b. The s minus 2 goes away, and we're left with s plus 1. Alright, we have this now. We can just try to solve it. Alright, well, there are two different ways to solve partial fraction decomposition problems, and I'll assume that you already generally know them, or if you don't, I'm just going to follow along with the way I'll do it, because this is what I myself find to be a little bit simpler. What we're going to do is we're going to vary s. We're going to say first, let s equal 2, for example. And the reason I picked 2 is that when we plug in s here, this is going to go to 0, because 2 minus 2 is 0. And we're not going to have to worry about that a term. So if I let s equal 0, what we get is, sorry, not s equals 0, s equals 2, so that this goes to 0. If I let s equals 2, we get negative 2 minus 7 is negative 9 equals a times 2 minus 2. All right, but that's just going to go to 0, which is nice. And that's the entire reason we picked s equals 2 for our first s, plus b times s equals 2, so 2 plus 1 is 3. So this tells us that 3b equals negative 9, or that b equals negative 3. If we just do some division, b equals negative 3 is our first constant. We got it. We know that this is now going to be plus 3 over s minus 2, making good progress. Now, let's plug in the second s that just makes sense to plug in, which is negative 1, so that this part goes to 0. Let's let s equal negative 1. And in general, you could use other values of s, but these just make it so much simpler. Why not use them? So negative 1 is plus 1, minus 7 is negative 6. That's this hand. The left-hand side is negative 6 equals a times negative 1 minus 2 is negative 3, plus, and then b times, well, now it's just negative 1 plus 1. That's just going to go to 0 again. So what we're left with is that negative 6 equals negative 3a, or dividing by negative 3, that a equals positive 2. Fantastic, we solved for our constants. If we just scroll down here, we can now say with finality and confidence that negative s minus 7 over s plus 1 times s minus 2, given the algebra we just solved, we know this has to be true, equals a, or 2, over just s plus 1, minus 3 over just s minus 2. And if we recall that we were actually trying to solve for the inverse Laplace transform of this, I'm just going to copy this so it's simple. Therefore, the inverse Laplace transform of this entire thing is going to be exactly equivalent to the inverse Laplace transform of this partial fraction decomposition, 2 over s plus 1 minus 3 over s minus 2. All right. And now, if we break this apart by our properties of linearity, we're going to get that this equals 2 times the inverse Laplace transform of 1 divided by s plus 1 minus 3 times the inverse Laplace transform of 1 over s minus 2. And if you're astute, you might have noticed I kind of extended the definition of linearity, or the property of linearity, from the Laplace transform into the inverse Laplace transform. And I won't prove it here, but it does turn out that the inverse Laplace transform is linear. It has this property of linearity, although I don't actually know how to show it. I've just been told. So the inverse Laplace transform has this property of linearity. We use it, and we're left with this. And now we can use our inverse Laplace transform properties that are much simpler. For example, 1 over s plus 1, 1 over s minus 2, those are in the form that we need. And again, we're just looking for patterns and matching them up to what we know from our Laplace transform properties. And our Laplace transform properties tell us that the actual Laplace transform, not the inverse, the Laplace transform of, if you recall, e to the at. Laplace transform of e to the at is the same as the Laplace transform of 1 times e to the at, which means the Laplace transform of 1, but shifted, so evaluated s minus a, equals 1 over s minus a. That looks like exactly what we have here. So what we can say is that this equals 2 times the inverse Laplace transform of 1 over s plus 1 is just e to the, and then s minus a. Minus a is plus 1, so a is negative 1. So e to the negative t. And then here we have minus 3 times inverse Laplace transform of 1 over s minus 2. S minus 2 means negative a is negative 2, so a is positive 2. Minus 3 e to the 2t. And that is how we can find inverse Laplace transforms of even slightly more complicated rational fractions with partial fraction decomposition. In the next video, I'm going to actually show you some examples of using the Laplace transform to solve real differential equations. It's going to be good. I'll see you then.